Okay, so we're going to talk a little bit about rational functions, which are going to lead to another type of, uh, which are going to lead to a certain type of field extension. Um, so really, rational functions is shorthand for rational polynomial functions, in how it's normally said. But we just say rational functions, and rational means like rational numbers. What are the rational numbers? Well, they're quotients of integers. So what are rational functions, which are really rational polynomial functions? They're quotients of polynomials. So we're going to describe two different sets here. We've already encountered this set, C adjoint, polynomials in T with coefficients in C, um, which I may say is C adjoint T, which is confusing because I've already said C adjoint for parentheses notation as well. Um, so it's clear, it should be clear from context. So in this case, this is polynomials, a set we've already looked at. It's in fact a ring, a domain even. And so it's all expressions that look like that. This ring or domain, excuse me. It's a domain but not a field. And you'll prove this in your homework. Namely, a multiplicative inverse for t doesn't exist. In fact, more is true. If the degree of your polynomial is at least 1, then the multiplicative inverse for p also does not exist. So it's missing all multiplicative inverses besides the obvious ones. The obvious ones are the constant polynomials, where it's just 1 over the constant. So it's missing all these multiplicative inverses. So what do? Well, we just add them in, right? How do you go from z to q? Well, you just add in the multiplicative inverses. And you do it in an intelligent way, but you essentially just add them in. So this passage from the polynomial ring to a new set where we add in the multiplicative inverses changes the bracket to a parentheses. This is called the field of rational functions over C in the indeterminate T, but I'll give you a set theoretic description first. So it's P of T over Q of T, where P of T and Q of T are in C adjoint T, and Q of T is, of course, not 0. And really, it's up to equivalence. Up to equivalence. And what's the equivalence? Well, equivalent fractions. So for example, like 2t over 2t squared plus 2 should be the same as t over t squared plus 1, right? Those are equivalent fractions. And this is the field of rational functions over C in the indeterminate T. We'll show it's a field here in a second. Let me just compare, just to hopefully make us feel a little bit more comfortable. I'm going to compare with Z and Q for a second. Namely, Q is the collection of all P over Q, where P and Q are in Z, and Q is not 0. And of course, it's up to equivalent fractions. So it's the same thing, right? Z is a domain. It's a commutative ring without zero divisors. We look at fractional expressions in Z. We get the rationals. C adjoint T, the polynomial ring here, is a domain. We look at rational expressions in that domain, which is just quotients of elements of that domain. We get this field of rational functions over C. Okay, so it's the same exact process. And I mentioned this before. I'm going to mention it again. If D is any domain, there's sort of a canonical or a natural field that you can attach to D called frac D. And it's a set of all expressions P over Q, where P and Q are in D, Q is not 0, and up to equivalence. And this is a field called the field of fractions of D. In particular, frac Z is Q, and frac C adjoin T is C parentheses T. Okay. Again, you don't need to know that, but it is kind of it's good to know that this is a general process. It's not just, oh, it happens in these two times. It happens in general. Okay. All right, let's do a quick proposition here. Proposition C adjoin T is a field with the usual addition and multiplication. Proof. All right, unfortunately, we cannot apply the subfield test. We cannot apply the subfield test because C adjoin T is not a subfield of C. So there's no there's not an ambient field that we have established as a field that this guy is a subset of to apply the subfield test to. Sorry, I said that in like the most complicated way. So what this means is, since we don't have access to the subfield test, we have to do it by hands. And that's okay. A lot of the checks are going to be simple. So we'll start with addition. Okay, so what's the addition? Well, it's P of T over Q of T plus R of T over S of T is find a common denominator, so you cross multiply. So that's P of T S of T plus Q of T R of T over Q times S, right? That's how you add fractions. Okay, so that's the addition rule. How do you show it's commutative? So let's do commutative. I'm only going to do some of them because you'll see very quickly that the proof that this is a field is the same as the proof that Q is a field. So if you go in and you look at a proof that Q is a field and you change all of the P's and Q's to P of T's and Q of T's, it's exactly the same. Okay. Let's show it's commutative. All right. Well, we just worked out P of T over Q of T plus R of T over S of T. So let's now work out R of T over S of T plus P of T over Q of T. So the rule is you find common denominator. So that's S times Q. So I have to multiply the first expression by Q over Q and the second expression by S over S. And then we're left with this. Now, the numerator and denominator are arithmetic of polynomials. Arithmetic of polynomial expressions satisfies all of the domain properties. In particular, it's commutative, no zero divisors and whatnot. So the numerator is equal to the numerator here because we have the same terms, right? So they're equal. And the denominator is also equal because it's multiplication of polynomials is commutative. All right, so addition is commutative. Let's see that we have an identity. I'm going to avoid associativity because it's terrible. What's the identity? Well, it's 0 over 1. 0 over 1 plus P of T over Q of T is we cross multiply, right? So 0 times Q plus 1 times P all over 1 times Q. This guy here is zeroed out. And so what do we get? We get 1P over 1Q, but 1P is P and 1Q is Q. All right, so there's an identity. Inverses. Well, what do you think the additive inverse of P of T over Q of T is? Well, it's negative P of T over Q of T. And how do you check that? Well, you use the rule. So we cross multiply. Actually, they have the same denominator, so we can just add them. It's equivalent to just adding them. And P plus negative P, well, negative P is the additive inverse of P in the polynomial ring, so that's 0 over Q. But 0 over Q is equivalent to 0 over 1, because when you cross multiply, you get the same thing. All right, so I won't do any of the multiplication, but it's similarly done. using the rule that when you multiply two fractions, I guess I don't need to put it in parentheses. Using the rule when you multiply two fractions, you multiply the numerators and the denominators. Don't overthink it. It's not hard. Associativity is even easy here. It's not easy with the addition, but it's easy here. All right. So it is in fact a field. You can go through the rest of the checks, but if you've forgotten or you get stuck, all you do is you look at a proof that Q is a field, and you replace all of the symbols with that symbol of T. That's it. And this is the field of rational functions or rational polynomial functions in the indeterminate T. Let me notice one last thing here. C is naturally a subset of C adjoin T via constant polynomials, and C adjoin T is naturally a subset of rational functions in T via guys that have denominator 1. And so we have a big subset containment where we view a complex number as that complex number over 1. It's a rational function in T. It's a constant function. So left-hand side's a field. The right-hand side's a field. This is a field extension. This is somehow a very large field extension. Well, it's not the largest, but it's a larger field extension than what we were looking at. As we take C, well, that's also not true. Let's not get into the set theoretic infinity stuff, but this is a large extension. As we take C and we add in this indeterminate T, we're going to give this type of extension a name shortly. This is one of the two main types of extensions that we're going to care about. This is called a simple transcendental extension, which is in contrast, let me scroll up here for a second, to these types of extensions here where you add in sort of a solution to a polynomial equation. Okay, so it's a different type, but we'll see they have, well, it's a slightly different type. They're both obtained by adding in one thing, but one leads you off to infinity and another satisfies a polynomial equation, so it sort of wraps back around.